Kia ora guys. We're going to have a look at pages 52 to 57 from the Walkermaths book, and the idea is anti-differentiation. And the best way to understand anti-differentiation is we'll start off by just reminding ourselves about differentiation. So on Desmos over here, I've got a function, so it's f of x equals 2x squared plus 4x plus 2. And how do we differentiate this function? So what we do is we start off with, we've got our y equals something like axn, so I'm going to do a generalized thing, and then when we differentiate we go to dy by dx equals, we multiply by the power and then we reduce the power by 1. Right, so let's write out a couple of steps there. So step 1 is we multiply by power. Ooh. Right, we do this here, and then we reduce power. Oh, I wonder if you guys can read that. Yeah, you can. By 1. Right, and that's over here. So let's do that process to this function here. So we write, this is just notation by the way. See, I've got y dy by dx. I'm going to go from f of x, and notation we just go f dash of x. So let's just do that process. So we've got 2x squared, so we're going to multiply by the power. 2 times 2 is 4, 4x, and we're going to reduce 2. We're going to reduce that power by 1, so that just becomes 4x. And over here, multiply by 1, the power is 1, it's x to the power of 1, and then we reduce, so x to the 1 becomes x to the 0, so the x disappears, so it becomes 4x plus 4. Alright, so that is what we've been learning. This is differentiation. Alright, I'm just going to call it diff because I can't be bothered writing too much on this piece of paper. Right, this is differentiation. So if we want to do anti-differentiation, we're going to do this process backwards. So what we're going to do is we're going to start with dy by dx, and I'm going to give you a new kind of bit of notation, and we're going to call it again ax to the n, because that's what we're starting with this time. Right, so when we go and try and anti-differentiate, we're going to need some different rules. So what we're going to need to do is we're going to look at these rules that we were following here, and we're going to have to do them in absolute reverse. Right? So let's start, instead of starting from step 1, we're going to have to start from step 2. So we're going to have to do the opposite of reducing the power by 1. So that's going to be increase power by 1. Right? That's going to be step 1 when we anti-differentiate. So let's do that. Oh, no, we'll do it in a sec. Right, we're then going to have to do step number, we're going to do this in reverse. So now we're going to go do step number 1. And instead of multiply by the power, we're going to have to do the opposite of that. It's going to be divide. But actually, we've already increased the power by 1. So we're going to have to divide by new power. Right? So to be able to do these steps in absolute reverse, this is how we're going to have to do it. Instead of reducing the power by 1, we increase the power by 1. And then instead of multiplying by the power, we divided. And because we've already done step number 1, we're dividing by the new power. So let's do that. So step number 1, it's going to be axn, and we're increasing the power by 1. So it's going to be n plus 1 here. Right? And then we're going to divide by the new power. So we're going to do all of that over this new power here, which is n plus 1. So that's the rule we're going to be following for anti-differentiation. Right? So we're starting off with f dash of x equals 4x plus 4. So let's apply the rules to that. So it's going to be f of x, because we're going from f dash of x, and we anti-diff. I'm going to write that up here. Anti-diff. Right, so we've got 4x. So what do we need to do? We need to increase the power by 1. So that's x to the power of 1 right now. So that's going to be 4x squared now, because we increased the power by 1. And then we're going to divide by the new power. So we're going to divide it by 2. I'm going to fix that up later. Don't worry, I'll do it another time. Let's do this one here. Plus 4, so it's going to stay as a plus. We're going to increase the power by 1. So it's x to the power of 0 currently. And so that's just going to become x to the power of 1. And we divide that by 1. We've got, if we divide that by 1, it's just the same, right? Let's fix up this one here. So that becomes 4 over 2 is 2. So 2x squared plus 4x. Surely we're done. No, there's actually a secret step number 3. We have to add in a step number 3. Because if we look at the original function that we're trying to get back to, look at this, 2x squared plus 4x, it matches 2x squared plus 4x. But where the heck does this 2 come from? Right? So there's this constant that when we differentiated, that disappeared, right? We can't work out where that constant is because we can't see anything with this plus 0. So there could be a constant here. And there is in fact a constant here. But there's no way for us to work it out. So what we do is we just add in a letter to represent that constant. And maybe we get more information later on to find it. So we're going to add in a thing called plus c. And that just means a constant of integration. So when you anti-differentiate, there's this constant that could be floating around, so we just put a plus c to make sure that happens. If you look on maths memes on the internet, they are loaded with people forgetting to do the plus c when they integrate or when they anti-differentiate. So let's make sure we add that plus c. I want you to look up a few memes for me maybe later on. So we're going to need to add constant. Right, that's step 3 when we anti-differentiate, add constant. That plus c is really important. Okay, so the question now begs, how do we find out about that plus c? So on the screen, I'm going to write up a new question. All right, so let's say we had a function that was 4x plus 4, right? And we got given the instruction, find the original function if 4x plus 4 is the derivative. The original function passes through, and we're going to go -3, 8. Right, so I'm going to put in that -3, 8 there. -3 and 8. You should be able to see that up on the screen. OG function through here. Alright, so we've got the derivative, which is this red line. And we know that the original function passes through here. So let's see if we can find that out. I'm going to just move that up there for you. So we'll use the, we found this out already. So we would have got 4x plus 4 as our derivative. And then we did integration or anti-differentiation to get here and here. So now let's put that in. So we've got 2x squared plus 4x plus c. So we've got this constant. That means, so we've found out that the antiderivative is a parabola. Let's make it a little bit prettier. I'm going to go blue. And I'm actually going to make this original derivative dotted. Right? And we're going to move this c around until it passes through that black dot. And you'll notice there's only one c that satisfies that condition. There's only ever going to be one c that makes it work. Well, maybe that's not entirely true. We'll look at that later anyway. Right, so what we're going to do is we're going to find it algebraically rather than just using a slider on Desmos, because we could just do that and we know that c equals 2. But we'll find c equals 2 using a bit of algebra. So let's go to a new page because I've run out of space. So we have this function. This is the original function, f of x equals 2x squared plus 4x plus c. And we're looking at the point -3, 8. right? So all we need to do is simple substitution actually, and then that's just going to find us c. So let's do that. So -3 is going to replace our x's, and then 8 is going to be f of x. So we're going to write 8 equals 2, and then in brackets -3 squared plus 4 -3 plus, and then there's our unknown, or our constant of integration. So let's go through and work that out. So I like to keep things tidy when I can. -3 squared, -3 times -3 is 9. So 2 times 9 is 18. 18 plus 4 times -3 is -12. Whoopsies, I should have put a minus there. Oh well. Plus c. We're going to keep c on the right because it's already positive. So -12 going over here, that makes it 20. 8 plus 12 is 20. And then 20 minus 18 gets us to 2. So therefore 2 equals c. So our original function is going to be f of x equals 2x squared plus 4x plus, and now we know what c is, it's 2. Nice. So yeah, that's anti-differentiation. I feel like I should give you guys one more example because maybe you'll still be confused, but it's kind of hard to think of something on the fly. You know what? I'm going to steal a question from Walkermaths. Why not? Yeah, that's right. You get one of the answers. Let's have a look at maybe one that's harder. Let's have a look at page 57, question 9. Q9. Just randomly selected. It's the second hardest. The derivative of a function is given by, so we're going to write dy by dx equals -2x minus 36x squared. And the function passes through the point 1, -4. So I'm going to write up here at, I love using this at symbol. Don't worry, it's totally not a thing that mathematicians do. I just really enjoy it. 1, -4. I'm going to write OG for original at 1, -4. Okay, so let's have a go at this. I'll model it up on Desmos in a second. But we'll start off by just doing our anti-differentiation. So we'll go y equals, and so what we need to do is we add 1 to the power and then divide by the new power. So it's x to the power of 1 right now, it becomes x squared, and so it's going to be -2 divided by 2 because the new power is 2. So that's just going to make it -x squared. I don't want to do too much working because I want to leave some space. Then it's going to stay as a minus. This power is going to increase by 1, so it becomes 3, and then it's -36 over 3, which makes it -12, and then we'll keep that power. X to the power of 3. Are we done? No, what do we forget? We need our constant of integration. Now, I like to change the letter every now and then. If you've already used C in a question and you need to change, like have a new constant of integration, why not use K? K is a kind of cool way to spell constant, who knows? All right, okay, cool. And we know that it passes through 1 and -4. So let's just substitute that in straight away. So it's going to be -4 for y, because that's our y value there, equals -1 squared, because 1 is our x value, minus 12, 1 to the power of 3, plus k. Oh, these are super easy. Okay, -4 equals -1 minus 12 plus k. So that makes -13. Chuck that over here, that becomes a positive 9. 9 equals k. So therefore our function is y equals -x squared minus 12x cubed plus 9. Let's have a look and confirm. Actually, we're going to do it backwards just to confirm, eh? So -x to the power of 2 minus, whoopsies, 12x to the power of 3, and then plus 9. So what we'll do is I'll make that a function. And zoom out Desmos to make it look prettier. Still a little ugly. Oh. Let's check that that passes through 1 and -4. Yes, it does. So you can see that it passes through that point. So we must have got our substitution correct. Now let's see what our derivative is. F dash of x. And does that match our original one? Let's check it. -2x. I'll make that dotted. -2x minus 36x squared. And look at that. See how that line exactly matches the derivative we started with? So we can confirm that that is in fact correct by looking at Desmos. Sweet. So that's all for me today. I'm just going to remind you guys to include the constant of integration. You will make that mistake at least once in your life. That's guaranteed. So when we're anti-differentiating, what we're doing is we increase the power by 1. We then divide by the new power and we add a constant on. Cool. There you go.